So very good evening to you all. I welcome you all in this lecture of KTG and Thermodynamics part 2. So this is going to be a second lecture. Okay. I hope you have enjoyed your holiday with so much of enthusiasm. Okay. So that same enthusiasm I will expect you for this class also. Okay. So in the lecture 1, if I talk about what we have discussed, we have mainly discussed about the pressure of a gas or ideal gas exerted on the walls of a container. Okay, kinetic theory of gases we have discussed, and also what we have discussed, the kinetic interpretation of temperature, like temperature in terms of kinetic energy, and we have also seen the expression of the total internal energy of a molecule in terms of temperature, which is 3 by 2 kb into T, where kb is the Boltzmann constant. So this all we have discussed in the previous lecture. Today we are going to revise first of all the few pointers from previous session, and then we will going to start the new concept of this chapter. So firstly, we know that the pressure inside an ideal gas is given by P is equals to 1 by 3 rho of gas. Rho means density of gas multiplied by the VRMS square, where VRMS is the square root mean square velocity, and I have discussed you for that you need to, this is the velocity, first you have to square it. Okay, then you have to take the mean of this, and then you take the square of this velocity. So this resultant is termed as the VRMS, root mean of square. Okay. Now the temperature of an gas is due to its motion VRMS. We also know that the temperature is nothing but the kinetic energy possessed by a molecule. Okay. So we can say that this V square RMS is directly proportional to T, or simply you can say that V is directly proportional to root T. VRMS is directly proportional to root T. Okay. So let's say, for example, if the comparison of two gases VRMS is given to you, so what you can say that VRMS of 1 divided by VRMS of 2 is equals to square root of T1 by T2. So these types of question are generally being asked in the examination, because I'm going through the previous year question of JEE Mains and NEET. So there are plenty of question which is coming out from this topic, which is VRMS is directly proportional to root T, directly from this formula. Okay, first just a little modification is there. Instead of T, you can put this as RT is equals to PV from the ideal gas equation. So this would be the resultant. Okay. So VRMS, we know that it is 3 square root of 3 RT by M naught. So these three formula you need to remember. First of all, the kinetic energy in terms of temperature, 3 by 2 kb into T. This one, pressure is nothing but 1 by 3 rho of gas VRMS square. This one, VRMS is root 3 RT by M naught. Okay. The most probable speed of a gas, VMP. Most probable speed is nothing but the speed possessed by the maximum number of molecules. Okay. This is the speed by which maximum number of molecules are traveling. Okay. So VMP is given by root 2 RT over M naught. Average speed is given by 8 RT by pi M naught. So these three velocities and their formula you need to at your fingertips. Okay. Because directly questions has been asked from these formula in your examination. Okay, so what is the loss? Nothing. Just to remember these formula and apply the concept and get the answer. Got it? So although you can do a little modification in that also, VRMS you can say, remember, it is 3 RT by M naught. M naught here is the molecular mass. Okay, so we can apply a relation. This R is nothing but Kp, which is the Boltzmann constant, multiplied by the Na, which is Avogadro's number. Okay, so R is the specific constant, universal gas constant, which can also be written as Kb into Na. So if you put this information in VRMS, so what you will have is 3 Kb Na into T divided by m naught. M naught is the molecular mass, or you can say the mass of how many number of molecules? Na. So you can also write as mass of one molecule and the total number of molecule, because molecular mass is nothing but the mass of one mole of gas. Okay, and in one mole, how many numbers of atoms are there? So it is Na, 6.023 10 raised to the power 23. Now you can cancel out Na here. So VRMS is equals to 3 kpt over m, where m here is the mass of one molecule. Mass of one molecule. Okay. So in these terms also you can remember the formula. What it? So these three formulas are very important, and two in the previous slide, which is, I will write it here. The pressure. Pressure is 1 by 3 times rho VRMS square. This one. And internal energy or kinetic energy simply is 3 by 2 kb into T. So these are very important formula. Direct question has been asked from these formulas. Okay. So now degree of freedom and energy of gas. This is the topic for today. What is our learning objective for today? Is degree of freedom, law of equipartition of energy, specific heat capacities of gases. Although we have covered this topic in thermodynamics also, but we will elaborate it more, because in kinetic theory of gases and in thermodynamics also, if this is a good question has been asked in JEE main, let's say, so they will also specify that what type of gas is doing work. Is it monoatomic, diatomic, triatomic, polyatomic? Okay. So for that, the specific heat capacity of the gases will change according to their atomicity. Got it? So here the specific heat that we are going to learn will also describe that what type of gas is it. Okay. Is it a diatomic gas? For that, the specific heat capacity has a different value. For monoatomic, it has a different value. And for polyatomic, it has a different value. Okay. And also for solid also. Then we are going to learn about the mean free path. Mean free path is the simplest yet very important concept of this topic. Okay. If you are expecting one question from mean free path, na, it is just a gift to you, because it's a very simple topic. Now, degree of freedom and equipartition of energy. What is a degree of freedom? Look, if I have a ball, if I have a ball and this is the rod, or you say this is a straight line. So if this ball is moving in this direction and this direction, so only one type of motion it can possess, which is the translation motion along the one dimension. Now, if I consider a plane, so this ball can move up and down. So there are two motion, which is also translation. I'm not considering any rotational motion of this ball. Okay, because ball you can consider as a point mass, and point mass has a zero rotational motion. You can't consider the rotation motion for point mass. But if you see in this example, if it is moving along a rod, which is a straight line, so it can only have a translational motion. Translation means shifting from one point to another point without rotation. Okay. So if I want to stop this ball, what will I have to do? How many dimension I have to cover? Only one dimension. I have to apply the force in one dimension only. But if I talk about this second degree, this plane, yx plane, okay. So if I need to stop this and I want to ensure that this ball does not move, I want to ensure that this ball does not move. So I have to ensure that in two direction I have applied the force. Okay. So that here where the degree of freedom is came. Degree of freedom is nothing but how many how many types of motion a ball or any particle can possess. Okay, that is termed to be as the degree of freedom. So if I talk about the straight line, how many type of motion is possible in that? Only translation, one dimension, in one dimension. If I talk about a plane, so two dimension motion can be possible in y-axis and in x-axis. So there are two degree of freedom. If I talk about the three-dimensional axis, so you can translate this point mass particle in three axes. So there are three degree of freedom. Okay. Now, if the particle is rotating also, that also that also include in the degree of freedom. Okay. So if I talk about the definition of this degree of freedom, it defines as the total number of independent variable that is required to describe the position and configuration of the system. So if there is a motion which is occurring in straight line, how many position coordinate you need? You need the position coordinate of one axis also, one axis only. But if it is a plane, so you need two coordinate x and y. In three-dimensional axis, you need three coordinate x, y, z. Okay. So degree of freedom is the total number of independent variable. These x, y, z are not dependent on each other. So they are independent variable that is required to describe the motion or position or configuration of any system. So that is why the degree of freedom for straight line or one dimension, it is only been one. For plane, it is two, and for three-dimensional motion, it is three. Got it? Now for translatory motion, particle moving in a straight line along its any one of the axis has 1 degree of freedom. Like for example, this ball. So you need only one coordinate along this axis to describe the position and configuration of the system, which is this ball. Got it? So there is only 1 degree of freedom. One freedom means how many it can move freely in the space, in how many dimension. So in one dimension it can move only in one direction freely. So there is only one coordinate that we need to describe, so that is why the degree of freedom is 1. If I talk about the planar motion, so you can see that these insects are moving up and down randomly in straight line motion and all. So they are having a planar motion. So we need a particle moving in a plane x and y axis has 2 degree of freedom. Okay. Now a particle moving in a space xyz has 3 degree of freedom. Okay. Or you can understand this degree of freedom in the opposite manner. Like if you want to stop this ball, so in which direction, in how many ways you need to stop this ball? Only you need to apply the force in this direction along the motion of it. If you want to stop these insects, so you have to describe your motion or your stoppers in two direction. So there is 2 degree of freedom. And if you want to stop this bird which is flying in the sky, so what do you need to do? You have to manage the three coordinate axes x, y, and z. That is how you are going to stop it. Okay. Now for rotational motion, so point mass cannot undergo any let's say any rotation. Okay, because this is the point mass. How you can describe this? How you can describe the uh, rotational motion for that? So point mass possess only translatory motion, not rotational. But the rigid body that we have studied, this is the rigid body in system of mass and rotational motion. So this rigid body, it can possess the translation motion about any axis. Okay, and translation also. So for rigid body, there are two possibilities for rotatory motion and translatory motion. Okay. Now this rotatory motion. can also have three coordinate in space. How? Let's say this is the road that we have. Just a second. So this is the road that we have, and these are the three axes: y, x, and z. So it can rotate about y-axis, it can also rotate about x-axis, it can also rotate about z-axis. So there are three possible coordinates in space for rotatory motion also, which means if a body is, let's say, translating in one dimension and also rotating in that dimension, so how many degree of freedom that body can have? Anyone? Answer? We have discussed that if a body is moving in a straight line, just moving, only translating, so it need only 1 degree of freedom. Okay, it has 1 degree of freedom. But I am saying that if it is translating in one dimension, only one dimension, and rotating also on that dimension also, but only one dimension. Okay, so how many degree of freedom it possess? Anyone? Ganesh, Karthik, Shreya, Bhaskar, any one of you can guess? Like, just a second. If this is a system, let's say these are two balls attached with this rod. Okay, so they can move in this direction, up direction and z direction. In how many way they can rotate? This system, how many way it can rotate? It can rotate about this axis like this, like this. It can rotate about this axis, and it can rotate about this axis also. Okay, so only two types of rotation will be there. One is like this, and one is like this. Okay, so how many degree of rotational it possessed? Without, how many degree of rotation it possess? Anyone can guess? It's very simple. So it possess only 2 degree from the rotational motion. Okay, so total degree of freedom is 5 there. 3 translation about 3 axis, and 2 is the rotational motion. Got it? Now, the rigid body can have 6 degree of freedom, 3 due to translatory motion and 3 due to rotatory motion. Got it? And the system that we have, this is the maximum number of degree of freedom that a rigid body can have. Okay. Now, what is the law of equipartition of energy? Law of equipartition of energy says that for any dynamical system, okay, which is in thermal equilibrium, the total energy you can equally distribute in all possible energies mode, which is degree of freedom. Okay, in simple word, any particle, the distribution of energy is directly proportional to the degree of freedom. Okay, whatever the number of degree of freedom that particle possess or that system possess, in that many ways the energy is distributed equally. Okay, so for example, we know that energy is 3 by 2 kb into t. Okay, and if the system is only translating, okay, there is only one ball, this is the system, so rotational motion we cannot consider for that, and not this is the point mass, so it can only move only in x, y and z axis. So it can possess 3 degree of freedom. Okay, so it can move in x axis, move in y axis, move in z axis. This is the total energy. Okay, so this total energy according to law of equipartition of energy it is distributed to all possible movement of it. So this energy is distributed in three ways. So for one way, the energy will be 1 by 2 kb into T. For second, for let's say y-axis, 1 by 2 kb into T. And for z-axis, it is 1 by 2 kb into T. Okay. So this is the law of equipartition of energy. Got it? Now for that, how do we know that system has how many degree of freedom? It depends on that what is the system. Okay. Does the system have only one point mass, or the system has two particle, or the system has three particle, or let's say whatever the number of particle? Okay. So that is why we are going to this. So according to kinetic theory of gases, the mean kinetic energy that we have discussed in the previous lecture. So the mean kinetic energy of a molecule of monoatomic gas is 3 by 2 kb into T. Okay, this is the mean kinetic energy, and this is monoatomic gas. So monoatomic gas means only one molecule is there. Okay, so if this is the one molecule, so it can possess only three kinds of motion, only one kind of motion, but in three ways. It can only possess the translatory motion in x-axis, y-axis, and z-axis. So we can say that for each axis, let's say we talk about the x-axis. So this, the mean kinetic energy. So in x-axis, we can say the energy will be given by 1 by 2 mv square. And this is the mean. So we are taking the mean of this. So this energy is nothing but equals to the equipartition of this energy. If you divide it in three times, so it is 1 by 2 kb into T. Similar for the y-axis, the mean kinetic energy in y-axis mvy square, 1 by 2 kb into T. And similar for the z-axis mvz square, 1 by 2 kb into T. Okay. Got it? So, just a second. So these are the mean kinetic energy in each axis. So x, y, z, three axes we have taken. So in x-axis, this is the kinetic energy. In y-axis, this is the kinetic energy, and in z-axis, this is the kinetic energy. And this is nothing but the mean kinetic energy of a molecule, which according to the kinetic theory of gases is 3 by 2 kb into T. This will equals to 3 by 2 into kb into T. So because the molecular movement is very random, so we can consider that the speed and the elastic, there the collision between them is elastic. So we can consider that the movement or the velocities in each direction or the kinetic energy in each direction is same. So 1 by 2 mvx square plus is equals to 1 by 2 mvy square is equals to 1 by 2 mvz square. And this is equals to 1 by 2 times of kb into T. So you can say that this energy associated with each degree of freedom per molecule is half kb into T. Because this monoatomic gas molecule possesses only 3 degree of freedom. Why? Because it can only translate into 3 axes, not rotate. We are not considering the spin about its own axis. We are only interested in the translatory motion. So 3 translatory motion it can have. So we can say that it has 3 degree of freedom. So energy associated with each degree of freedom per molecule is half kb into. Got it? So if anyone has any kind of doubt, you can ask, or you can put your doubt in the chat box also. Now for monoatomic molecule, because it consists only a single atom. So it has 3 degree of freedom as I have discussed. For example, helium, argon. Okay. Now this way, it can move in x-axis only. X-axis this way. It can translate about x-axis, or it may translate about y-axis, or it may translate about z-axis. So it has 3 degree of freedom based on that molecular moment. Okay. So energy will be E total is half mvx square, half mvy square, half mvz square. So the average you will take is 3 times of 1 by 2, because for each molecular moment or each degree of freedom, what is the energy possessed by it? It is half kb into T. And how many degree of freedom it has? It has 3 degree of freedom. So the total kinetic energy is 3 by 2 kb into T. Okay. So if I talk about the internal energy of a monatomic gas, this you can also consider it to be internal energy. So for internal energy, N into Na has to be specifically multiplied. So this will become 3 by 2 nRT. Okay. Although you don't need to do that, only you will replace this Kb. I have talked about the formula that R is equals to what? Kb into Na. So if we put this here, 3 by 2, instead of Kb, we want to put R upon Na. So it will become 3 by 2 R upon Na into T. Okay, 3 by 2 RT upon Na. Now, for one molecule, this is for Na. So for one molecule, we will, for total number of molecules, we would multiply it with Na, because this is the total number of molecule in a gas, 1 mole of gas. So for 1 mole, we cancel it. So that is why you have 3 by 2 nRT. You can put the value of N is 1 here. Okay, so you will have 3 by 2 RT. Now for diatomic gas, the diatomic molecule can rotate about any axis at right angle due to its own axis. You will see in the emanation also. So it has 2 degree of freedom of rotational motion. I have discussed it. Okay. Additional to that, 3 degree of freedom of translation motion along the 3 axis. So it has 5 degree of freedom, 3 from the translation motion and 2 from the rotational motion. Now, examples for that is O2, oxygen, nitrogen, CO, carbon monoxide, and Cl2. Other also. Now, how they are possessing the 5 degree of freedom? So firstly, this is the diatomic molecule. So two molecules are attached. You can see here. It can move along the x-axis, no problem in that. Same way it can move along the y-axis. In same way it can move along the z-axis. But it can also rotate about its own axis in this way. Okay. This is also the one type of motion it is possessing. Okay. So this will also count as a degree of freedom. And this way it can also rotate. Okay, so only these two rotations is possible. Got it? Now, so these two rotation possesses 2 degree of freedom extra, 3 from this, 2 from that. So total degree of freedom will become 5. Okay, so the total energy will become here et means E from translation energy plus E rotational. So from translation, it is 1 by 2 mvx square vy, same expression. And for rotation also, it is half ix omega x square plus 1 by 2 half iy omega y square. This is the kinetic energy for rotation. For rotation, we give it 1 by 2 times I omega square. Okay. So this is rotating about y-axis. So we have taken Iy, and this is rotating about x-axis. So this we have taken as Iz. Okay. Now this is the ET and this is ER. So how many? So agar if instead with this translation and rotation also, if you put the gas in a very high temperature, the diatomic gas, so they can also grab some vibrational energy. Okay, but for a very high temperature. So we can also consider that. So for considerable vibration, they can also possess some kind of energy there. So what is that energy? They can also vibrate. Okay. So energy due to vibration is kinetic energy of vibration, because in vibration or oscillation, what do we have? We have kinetic energy plus potential energy. So kinetic energy of the vibration plus potential energy of two molecules. So it will be given by 1 by 2 mu dr by dt whole square plus 1 by 2 kr square, where this term is the term for potential energy and this term here for the kinetic energy. Okay. So if you will see in the previous energies, the translation and rotational. So for one axis only you have one square term only. This is also for Ix you have only one square term. For Iy you have only one square term for translation and for rotation also. But if you will see this expression, here we have two square term. One is for kinetic energy, another is for potential energy. So that half kBt, this is for the 1 degree of freedom. Okay, but it has now two potential energy. So this you can say it is half kBt plus half kBt. So energy due to vibration is become kb into T. Got it? So the total energy of the molecule now will become E translation plus E rotation plus E vibration. Okay. So this is the total energy expression for the for what? For a diatomic gas. Now this this is the translation, this is vibration, and this is translation, this is for rotation, and this is for vibration. Now for non-vibrating molecules, only 5 degree of freedom is there, 3 from translation, 2 from rotation. But so you can say the average energy of a molecule is 5 into 1 by 2 kb into T. So 5 by 2 kb into T. Now for vibrating, two extra term we have to add. One for kinetic energy, one for potential energy. Okay. So two extra degree of freedom it will possess also. So from that it is 7 and 7 into 1 by 2 kb into T. So the total energy will become 7 by 2 kb into T. Got it? Now, so you will remember this. For non-vibrating diatomic molecule, degree of freedom is 5. For vibrating diatomic molecule, degree of freedom is 7. So for total energy, you will have to multiply this degree of freedom with 1 by 2 kb into T. Okay. Now, for triatomic molecule also, you can have this 5 degree of freedom. For non-linear type of, it has 6 degree of freedom. This. Okay. So the average energy of the molecule is 3 kb into T. Now, this is the example. If n moles of diatomic gas in a cylinder are at a temperature T, heat is supplied to the cylinder such that the temperature remain constant, but n moles of the diatomic gas converted into monatomic gas. Then what is the change in the total kinetic energy of the gas? Now, these are the options. Now, firstly, what we will do, this is the kinetic energy initial, because it is a diatomic gas. It has been put in the cylinder at a temperature T. So heat is supplied to the cylinder, then what will happen? So the number of moles in the final sample will be 2n, because n mole we have converted into what? Monatomic gas. So final kinetic energy we will have 3 by 2 times 2n into RT. So change in kinetic energy final minus initial. So this is the final energy, this is the initial energy we have. So it will become, if you subtract it, 3 by 2 nRT. Got it? Now, now the specific heat capacity, and before that, I want to discuss the formula that you not need to rush about how to calculate degree of freedom. So degree of freedom is three n minus k, where n is the number of particle and k is the independent relation. Monatomic gas, what is the number of molecule is 1? So n is 1. So this one molecule possess only one zero relation, because it has no other molecule to relate with itself. So k here is 0. So if you do it in this, 3 into 1 minus 0, it will become 3. So we have done, see that monatomic gas possess only 3 degree of freedom in translatory motion. If I talk about the diatomic gas, so for dia the number of particle is 2 and relation is only 1, because these are the two particles. So are they relating with each other with only one way, this way. Okay. But if you talk about three variables, okay, got it. If this is the non-linear may you can relate this one. This is the one relation. This is relation number 2, this particle with this, and this is relation number 3. And these three relation are independent. When this and this are relating, this has no interest in that. Same way this, same way this. So number of relation here is 3 and number of particle here is also 3. So how many degree of freedom is there? So it will be 3 into 3 minus 3. It will become 3 into 2, which is 6. But if it is linear, like this, so how many relation is there? Only one relation, only one way you can relate that. Okay. So this will become 3 into 3 minus 1. Okay. So this will become, or let's say, just forget about it. Okay, we will learn it for non-linear also. Non-linear only. So this is valid for non-linear. I forgot to mention here. This relation is valid for non-linear molecules. So these are the only one relation is possessed by diatomic here. So number of particle is 2 into 3. Sorry, 3 into 2 minus 1. 3 2 just 6 minus 1 is 5. Okay. So for diatomic, the degree of freedom is 5. Now the specific heat capacity and mean free path. Specific heat capacity, by definition, we know it is the amount of heat that we supplied to the system to raise the temperature of the system by 1 degree Celsius. If it is molar heat capacity, a specific heat capacity to raise the temperature of a 1 gram of substance by 1 degree Celsius. For molar heat capacity, for 1 mole, if I want to raise the temperature of 1 mole, then it is termed as molar heat capacity. Now for monoatomic gas molecule has 3 degree of motion, or degree of, you can say, freedom. So this is the kinetic energy, 3 by 2 kb into T. So for 1 mole of such gas at constant volume, the internal energy will be constant volume. Got it? So this U is Na 3 by 2 kb into T. This is nothing but, if you differentiate this, let me do it here. So for monoatomic gas, for monoatomic gas, total energy or the kinetic energy, you can say it is 3 by 2 kb into T. Now, we only define Cv and Cp. This is the molar heat capacities. Cv is for constant volume, Cp is for constant pressure. Okay. When the volume is constant, there is no work done according to first law of thermodynamics. So delta Q is nothing but delta. So we can say that in that case, delta U is equals to NCV delta T. So Cv here is nothing but delta U by delta T. Same way we can do it here. If we differentiate this with respect to time, sorry, with respect to temperature, so du by dt is nothing but 3 by 2 kb. Now kb you can put at uh, r into na. Okay. And if you are calculating it for 1, so you have to divide it for Na. So molar heat capacity you will have as 3 by 2 into R for single molecule only. So this will become Cv. So Cv here is 3 by 2 into R. Now we know the relation between Cp and Cv, that Cp minus Cv is equals to R. This is termed as the Mayer relation. Mayer's relation or formula. Okay. So if you put the value of Cv here, Cp will become Cv plus R, and which is nothing but 5 by 2 times of R. Now you can also calculate the adiabatic index, which is gamma Cp by Cv. So Cp here is 5 by 2 R. Cv here is 3 by 2 into R. So gamma will become 5 by 3 for monatomic gas. So this is the way you can calculate it. Got it? Now, if you are interested that how this formula has came, Cp minus Cv. So it has came from the first law of thermodynamics. Also, you can derive it. Delta Q is equals to delta U plus plus W. Okay. If you differentiate these terms, so it will become delta Q by delta T, delta U by delta T plus dW by dt. Okay. So for constant volume, if volume is constant, so work done is P delta V. Okay. So this will become 0. Got it? Now, and also for not the constant volume specifically, it is delta Q by delta T, or you can say dQ by dt for very specific values. Du by dt plus d by dt into PV. P into delta V. So you can say for constant pressure, it is. So this PV can also replace by PV is equals to nRT. Okay. So this will become PV you can replace by RT. So d by dt of RT will become R. This dQ by dt is nothing but C of P at constant pressure. If you will see, Q is equals to U plus W. So at constant pressure, what is the specific heat? This total. So this total U plus PV is dq by dq. So this you can write it as Cp. Okay. But if you talk about constant volume में this term will become zero, the work done. So this Q is equals to U, and U is nothing but the U is equals to NCV delta T. So CV is nothing but U by delta T. So this is nothing but this CV, this is nothing but Cp. So CV is equals to Cp is equals to Cv plus R. Okay. Now, so this way Kb you can replace R by Na. So what I have also discussed here, all the things. This I have discussed already. So delta is 3 into R delta T for constant volume. So you compare it, this will become Cv 3 by 2 times R. Okay. And it is for constant pressure, it is Cp minus Cv is equals to R. This is the relation. Okay. This is Cp. Now ratio of Cp and Cv. So this will become 5 by 3, which is 1.67. These values need to remember. Okay. Now for diatomic gas, if I do it, so diatomic gases may we have two possibilities. What? Molecule is a rigid rotator. If it is a rigid rotator, which means it cannot vibrate. It is rigid, na, so it cannot vibrate. So due to vibration, these extra 2 degree of freedom we will not consider here. So only 5 degree of freedom is there. So if the degree of freedom is 5, 3 from translation, 2 from rotation. So we can say that total energy will become internal energy of a molecule 5 by 2 kb into T. Kb is nothing but R by Na. So Na we are cancelling because this is the energy possessed by only a molecule. And we are considering the total number of molecule. So total number of molecule in 1 mole is Na, Avogadro's number. So we will multiply it by Na. So the denominator Na will cancel out. Now the internal energy at constant volume is mu Cv delta T. Now mu Cv delta T or T is equals to 5 by 2 into RT. So from that you can say that Cv is nothing but 5 by 2 into R, because this is the molar heat capacity. So mu is the number of mole, which is 1. T is 1 degree Celsius. So Cv will become 5 by 2 R. In the monatomic, it is 3 by 2 R. Only you can add R. Okay, you have added R into that. And for Cp, this, for Cp you can calculate it is 7 by 2 R. So for monoatomic, Cv is 3 by 2 R. For diatomic, Cv 3 plus 2, 5. And 5 plus 2, 7. Only plus 2 you need to add. Okay, you can remember this relation by that formula. So for Cv is 5 by 2, Cp is 7 by 2. What is gamma? So gamma is Cp by Cv. So which results in 7 by 5 for diatomic gas or 1.4. Now, when molecule is not a rigid rotator, which means now the degree of freedom will become 7. Okay. 7 by 2 into RT. So you again going to calculate Cv, we have 7 by 2, only plus 2 you have to do. Okay. So if I make a chart na here for monoatomic, mono, dia, for mono dia, Cv and Cp. Cv is 3 by 2 for mono. Cp is 5 by 2 plus 2. And here also you need to plus 2. So you need to remember this plus 2 cycle. 5 by 2 for dia, Cv, this is Cv and this is Cp for mono and dia. Cp 5 by 2 plus 2 kar do 7 by 2. This is only for not rigid rotator. If dia is rigid, not rigid, Nr, dia. So plus 2 again, 7 by 2, plus 2 again. Okay, this way. Now, just a second. We will complete this chapter by today. So please be patient. So it is 9 by 2. Okay, so ratio is nothing but 9 by 7. For polyatomic gas, 3 translation is possible, 3 rotational because it is polyatomic, so it can rotate in 3 axes. Okay, but we do not know about how many ways it can vibrate. So we are considering it F. Now, if you calculate the total energy, 3 by 2 kb into T for translation, 3 by 2 kb into T for rotational, 3 into half kbt. Okay, and F into kbt for vibration, because for vibration we have seen it is kb into T, not half kbt, because it possesses kinetic plus potential also. So total energy you will have here 3 plus F into RT. Compare it with CV. So CV you will have 3 plus F into R. CP you have 4 plus F into R. Now, if you take the ratio, it will become 4 plus F into R divided by 3 plus F into R. Okay. For solid, so for solid, the vibration you can take is more, because in solid the atom do not move with the internal kinetic energy. They can only vibrate because they are fixed at their position. So kinetic energy of vibration plus potential energy of two molecules. So this will become 3 into T, 1 by kb into T. 3 kb into T, the total energy. So R, what is the CV you have is this 3R. Okay, and here we will not take the CP and CV. It is only C for water. So this point you need to remember, that for the purpose of calculation of specific heat capacity, water is treated as the solid. So we have 3 molecule here. So 9 degree, we have already seen it. Now the C is for water is 9R. We will see it later, this numerical. Firstly, we will see the mean free path. So I will give you the idea about mean free path. Mean free path is not a very big concept and all. Mean free path is when a particle collide, when an atom make a collision with another atom. After that collision, it will move free, and then it make the second collision. So the distance that it has been covered without collision or any two successive collision, that distance is the mean free path. Average of that distance is the mean free path. Mean free path. So the kinetic theory of gases assume that molecules are continuously colliding with each other. So they move with the constant speed. That is why speed of the gaseous molecule is the order of speed of sound. But whenever there is a gas leak, it will take time to reach you. How and why? Because they are not moving in a single direction. They are moving in random direction and making collision, continuous collision. So that is why they will take time to reach us. Got it? So because they are not moving in a straight line. Now, so the molecule follow a chain of zigzag path. Zigzag path is like this. Okay. So each of these path is known as free path, which lies between two collisions. So I have already told you the path between any two successive collision, the average path is termed as the mean free path. So this is the random motion of molecule this way. They are colliding and then releasing. So this is the mean free path. Okay. So the average distance traveled by the molecule between all the collisions is known as mean free path. So this derivation is not so much of importance, although the result finally that we get is important. So if the molecule of the gas is there and having a diameter d, so we consider that one molecule is moving with the speed of v, the number of molecules per unit volume is n. Then the mean free path is L is equals to 1 upon root 2 pi n d square. So this formula you need to remember. Okay. So number of collision increases if the gas is denser or the molecule are larger in size. Okay. So as d is increasing, this L will decrease. Okay. So this is only this thing that I have to discuss. Okay. So this formula you need to remember this way. Okay. So this is it from my side for today. If you have any kind of doubt, you can ask. Otherwise, the lecture is being over and the chapter is also being over. Thank you so much for being attentive. Take care of yourself. Focus on your study. Prepare for your exam. Okay. Bye bye. Take care.